is. Today I will talk about these several sections. The first one we talk about this the background of the leads and what kinds of leads we build here, and the architecture, and then the implementation issues. And then I will talk about what kinds of attack and what kind of defense leads can provide. And finally, I will talk about how to secure the Linux kernel with the leads, and then a summary. And if any one of you have any question during my talk, you can just raise your hand. I can answer the question in the middle. All right, let's begin.
About attack and defense, is that attacks and defenses that leads mitigates or against leads?
All right, there are attacks against leads and attacks against the system. They are both.
So what will you be talking about?
Yeah, I will talk about the attack to the leads and the attack to the kernel and the attack to the system that leads can provide, what kind of methods that can prevent this attack.
Okay, so will you be talking about attacks against leads?
Yes.
If I have a system that has leads on it?
Yes.
Okay.
All right, here's the background. And I will talk about very quickly about this background kind of things. The very first one we talk about is the programs and the problems and current solutions to this problem. We face these internet ages, but we have seen a lot of hosts being hacked and defaced, and all the information being leaked and stolen kind of things. And there are lots of wounds and viruses spreading about this world, like the COVID and the Linda kind of things. And there are lots of vulnerability found every day. Even the very secure software like OpenSSH and Apache, recently they found a very serious bug. So what kinds of problem that we have made this problem occur? Even we have used some of the secure software like OpenSSH and OpenSSL kind of things, but we cannot prevent all of these problems. The reason for this is that the application software right now are not trustworthy, because more and more complicated implementation, because you have to meet the customer's requirements and you have to add more features to this software, and the software became more and more complicated, and you cannot avoid you cannot avoid the bug in the software. So the application software is not trustworthy. So you have to find a way to make this application, this untrustworthy application software became secure. And the kernel is not trustworthy. It means that I can just insert modules into the Linux kernel, and I can intercept all the system call, and I can do whatever things I want to do, even if the upper application layer, the application software is secure. And the third one is access control is not perfect. It means that right now, being a root or super user, you can do anything you want. You became a god in the system. So you can, if you can fire remote exploit code or use the local exploit, and you can become a root and you can do anything you want. So it's not perfect right now with the access control. Okay, the solution right here with the leads with our solution is we need a trusted kernel. This kernel can protect the kernel itself. It means that nobody can modify the kernel. Nobody can intercept the system call. Nobody can change it. And also this kernel will also provide this MAC. MAC is mandatory access control, and this MAC is not is different from what we have used in the Unix environment right now, and it means that no one can change the MAC rules, but somebody can change the rules that right now the Unix environment use. For example, if you can change the file, you can use change mode to change the file to, you can just say change, everybody can read it or everybody can write it, right? But as a root, you can change anything. So this is not very secure. But with the MAC, with the mandatory access control, no one can change these rules, even if as a root or super user. And with this MAC, you can implement the least privilege rules. It means that if, for example, for the etc password, this file is contain all the password in this file. Right now, everybody can read it because you need to read the password for the user to log in. But after logging, you never. This file is not useful to the users. So you can just make the login program to read this password file, and nobody can read it right now. So it means that nobody can read this etc password except the login program. Right now, the least privilege can implement with this mandatory access control. All right, the history of the leads just from the is about 3 years projects, and we have a lot of developers to help this project. Especially the core developer, Philip Bondi, he'll be here, I guess, and he had a talk yesterday. And also we have an FAQ maintainer, Steve Bremer, and I guess he'll also be DevCon 10. And there's another FAQ maintainer, Sandy Cray. All of these people help the leads projects to be growing. And we have add capability rules and lightweight MAC in the 2000 before in March of this year, we have also add LSM based versions. LSM is a Linux security modules, and will be added to the kernel 2.5 right now. I guess maybe in the next 1 or 2 months, all these LSM or Linux security modules will be added in the kernel. And we just talk about the background. And next we talk about the architecture that leads based on. The architecture here, there's a map here. All right. Leads contains several components. The core one is this access control models, and it contains the access control database, and it contains an administration interface, and it contains a hook checking centers. And when the user program, when the user program begin to execute in the system, he will fork, and he will use the fork and execv, this execv to execution. And right now the access control database will attach the access control list to the process, and when he try to access something, he will the lead will check with the access database, and then to determine if he can let this access continue or not. And we have divided the system into 2 categories. The one is subject and the other is object, and we place a checking between this subject and object. The subject is a process, and the object is all kinds of resources, such as a file, device, and all kinds of things that the process would like to access. And we have a log to log everything that maybe is related to the security. We have also an administration interface that you can manipulate the access control database. The features with the lead is that lead is a kernel patches It's a Linux kernel patch. Maybe in the future, it will be the Linux security kernel modules. And he implement a trusted kernel. And he have the Lightweight Mac in the kernel. And he have the admin tools. He include these admin tools use the IP chains like rules that is maybe easier to use for the users. And here we show an example. Well, it's not very clear. Say if you have logged into a system, you use the local exploit code or remote exploit code to get a root, and right now you want to try to get the shadow or get the password file. Right now, you just do a cat etc shadow at the very first line, and then before that, as a root, you can do anything. So you can see the shadow file, you can see all the contents, but right now, you can just the system will return as an operation not permitted. You cannot see the shadow file. You cannot cat the shadow file right now with the leads. And from the log, the leads we tell that somebody and with the UID, what kind of UID, GID, and what kinds of a program try to access this shadow file. And just another example is if you try to insert the modules into the kernel, maybe use the rootkit, some kinds of rootkit, and right now the leads will tell you that operation is not permitted, even if you as a root. And just talk about the architecture, and next we talk about the implementation. Do you have any question about this section? No? Okay, let's continue. All right, leads actually include several components, and include in order to implement these components, we have several very important structures. Here, the very first one is secure INO. This one is a global access control list. It means that everybody and any resource need to use this, need to check this ACL first. And there's a lead sys ACL also in the kernel. And this structure apply to individual process. It means that every process in the kernel got this lead sys ACL. It include all the rules, all the privileges that this process can got. And all these structures got the two significant structure. Here is the INO. This is the INO number and the DV number. This INO number and DV number identify a single file name or directory name or the device name kind of things. And we have also capabilities, and we have also all the ACL that this process contain. And this is the task structure in the Linux kernel structure. In the Linux kernel, this task structure is when the process is in the kernel, this process has a task structure, an only task structure to identify this process. And we have, for the leads, we add a pointer in this task structure with the lead system ACL. This means that when the process running under the lead LIDS control, he would got this lead sys ACL structures, and he would have this ACL, this structure will tell him that what kinds of access control lists that this process got, and what kinds of things he can do or he cannot do. And here we just go into the program and see when you do a fork in the program, and what leads do is he will inherit all the access control lists, all the access ACL from its parent. And you can see when you do the fork, we have the copy lead sys ACL, this function to copy everything from the parent. And after you do a fork, maybe you will do the EXE to actually execute this program. And from when you do EXE, we have lead set ACLs to set all the ACL that he gets from this program. So when a program is in a system, he will got two ACL. One is inherits from its parents. Another one is get from itself. For example, if a program, ABC program, this program have the privilege to read password file. But you use another program to execute this program. The other program is its parent. He got when this ABC running, he got the privileges, he got the ACL from his parents, and also he got the ACLs from itself, from the ACLs that he got. And after we have all the checking and all the process attaching kind of things, right now we will see a system call that we have the checkpoint. For example, there is an example is the change mode. When you use chmod, this system call, we have intercept, we have adding this checking in this system call in the kernel. You can see that this is if the red line one here is we add if leads check base. When this function do is he will check everything that this program got, and he will make sure that if this process had the privilege to do the change mode to the destination file, and if he do not get this privilege, we have a log here, lead security alert, and he will log everything that attempt to do this change mode. And here we say this function leads check base. Here we have this leads check base function, and this function is checking all the ACL database to see if this first you check if the destination file you can change that if anybody can change the destination file. If not, he will check if the program try to do the chmod, the change mode, had the privilege to do the change mode to this destination file. If he's not, he will just deny it and just return. All right. Does anybody have question about this section? No. All right. Just now we just talked about implementation issues. Actually, all these implementation kind of things, we have a how-to, but it's kind of obsolete. So I guess maybe in the future I will write another how-to to talk about these implementation issues. And next one we talk about the attack and defense with the leads. The very first one is we will attack the leads at the mean password. In the leads we have super user, right? The super user cannot do things that he can do before. So, but in order to admin all kinds of this access list control, you have to got the super users that he can do the privilege, he can do everything that the root can do before. In order to become this super user, you have to got a password. This password is installed in the kernel. So somebody will say that if I can get the password, I can do anything, right? But this password, we have several defenses. The first one is this password is 116 bits MD5. It's hard to guess. And another one, the second one is the most important one, that we have the restricted login TTY. It means that even if you know the password, if you just log in from the remote host, maybe you get a remote exploit code, you get a root from the remote site. But right now, even if you know the password, you cannot just become this super user, because we check the TTY. We check if you just log in from local or log in from remote site, or log in from a series port. We can define this these restrictions when you compile the kernel. And there's another way to modify the kernel's structure, the kernel's data, is use the raw I/O, the raw devices, just write, maybe modify the hard disk through the I/O operations. But right now, all the I/O operation is controlled by this cap sys root I/O capability. This capability has been disabled by default. So if you want to use, if you want to change the kernel by this DVK memory or DVK code, you cannot just write to these devices, because this cap sys row I/O has been disabled. The second one, we show that there's a lot of Trojan, a lot of rootkits and sensitive information leaking in this current years. The tag is included the Trojan. The first Trojan, if I can log in the system, I can modify this bin login, and I put the Trojans in this program. And next time when I log in, I will not use the password, right? And the log clean, maybe I just will clean all the log, because they will log something in this log directory. And we have the password. You can just store the password, etc shadow file, and you can use the other password cracking tools to crack it. And for the modules, you can insert or remove the modules from the kernel, and you can just insert some rootkits in the kernel, and you can modify the system core. And there's lots of kernel rootkits that can help you to hide your process, to hide your file. But the defense by the LIDS is that we can use file system protection first. This file system protection protection is implemented as a lead, and is in the VFS layer. It's a virtual file system layer, and he had the read only. You can set a file to only read only, that nobody can just write to it. For example, for this bin login, you can just set a rules that made the login to be read only. And in this case, nobody can write to it, nobody can change it. And for the log, you can just set it to append. So every log can append to this log file, but you cannot write it. And there's another mode is deny access. You can just set a file to deny access. It means that nobody can see this file when he do the LS or just modify this file. The example for this deny access is that you can set the etc shadow as a hidden file, so nobody can see it. And the modules operation, you can prevent, insert more, or remove modules from the kernel before if you are root. But right now, because all the modules operation is controlled by this cap sys modules, these modules has been disabled by default by the lead, so you cannot do anything to the modules right now. We saw a log here, and when you do the insert mode and the leads, we saw there's a log here. It means they show that which person and violate these cap system modules. So he can increase the kernel security by this way. And the next one is LD, this low LD preload kind of this LD preload can insert the malicious code in a process when this program runs. So in this case, if this program gets privilege from the leads, and I can just compile a preload library, and I can just insert this library. I can use preload, LD preload, and run run with this privileged program. And because this privileged program, maybe he can read the password file. Right now, I can write this library with the LD preload, and I can do anything as this privileged program. This bug is discovered by the Tesla team in the early this year, and we have a solution is that we check the LD in the environment P, because all the LD preloads is in the environment pointer. You can just check one by one, and we just check this LD and underscore, and we check if there's any LD kind of things. When the program is executed, we just clear all the ACL. So it means that you can still use LD preload, but you cannot get ACL, the leech ACL. So in this case, we made the system more usable and more secure. Another one is we have also a very lightweight shellcode detections in the kernel. You know, a lot of local exploit code, we use the shellcode to get a shell. And this shellcode we provide as parameters to the program or as an environment to this program. And what we defend is we check the shellcode is very easier. We just check some of the piece of the shellcode in the environment P or the arguments in the environment or the argument C. In this way, we can prevent shellcode in parameters and environments. Some of the examples that I just run this xlog exploit code. You can find this one in the on the internet. And when leech is on, when I run this exploit code, the local exploit code, and leech can find it, and he will say the shellcode detected when execute this file and program terminated. It means that when the program is running with the shellcode in the parameters or in the environment, leech can just terminate this program and the local exploit code. We can, in this way, we can prevent some of the exploit code, but it's not all of them, because if the shellcode, because we just check a piece of the shellcode, just like if you just like the system call kind of things. The next attack is a dynamic one-time kernel modification. This attack you can find in Flink magazine 58. Is very recent one, and you can they provide a method to modify the kernel code through this K-code or this DV K-memory, and he can modify the kernel's one-time database the data. In order to do this, he had to write to this proxy K-code, this file, and or this DV K-memory. He had to have the ability to write. So right now, the leads, what leads can do is he can defend it is just by this, we have talked about it, just by this cat6 row IO. This row IO is the capability that he had disabled by default. He control everything to access to this row IO file, include the hard disk, include all the drivers, all the row IO devices. And we have the log here. As example here is that when you try to do this write to this DV K-memory, the leads will terminate the system call and return an error and log this operation. Say you have violated this cat system row IO, so it can prevent this kind of attack. All right, we just talked about the attack and the defenses with the leads. And next we talk about this how to build a secure Linux with leads. all this information you can find on our website is www.lids.org. But right now, and you can get all the FAQ and all the how-to on the website. First of all, you need to get a vanilla kernel from the www.kernel.org and its mirror. A lot of people just send email to me said, why I cannot use Red Hat's kernel to patch, because we do not support Red Hat's kernel, because right now we only support the vanilla kernel. It's easier for us to maintain it. So you have to download the kernel from these websites, and you need the kernel. After you do that, you can download the kernel patch, our Linux kernel patch from our websites and all the tools. And if you want to use Linux security modules, you can just go to this lsm.inmunix.org. And after that, you can just after you untar this kernel source, you can do the patch, use the patch program to patch with our with these leads. And yes, the last one. After you patch the leads with the vanilla kernel, you can reconfigure the kernel. You have to use menu config, as config or config to reconfigure the kernel. There are several options in the kernel in the leads, and you can decide if you want to use it. And after that, you can rebuild the kernel and just install the kernel and compile and install all the lead tools, including these leads admin tools and the leads com tools. And we have the default ACL setting by default, but maybe you need to add the new ACL by yourself. There are several important directory for leads. The very first one is etc leads. This directory includes all the leads.com, leads.net, and leads.pw file. This file will be read when the kernel boot up, and he read everything in the kernel. And this directory is protected by leads by default. It says you cannot go into this directory, you cannot change this directory. Anything you cannot do this. You cannot do anything to this directory if you are not a super users. And there's a tools leads.conf. This tools is used to manipulate the access control list. You can just say leads.conf. I need a program. This is a subject. The program. I want this program can read a file or write a file. The -o is an object, and you can just say there's several options here, and you can also use the leads.conf to configure the capability, and with this inheritor level kind of things. The leads admin is used to do some administration tasks. For example, if you want to enable or disable leads on the machine, you can just log in and do this leads -s and dash leads. Here you need to provide a password, and then the leads can be disabled. And you need to this -i is to seal the kernel. This seal the kernel means that after I stop everything, I need the program, I need the SSD kind of things. After I do everything, I stop, stop the machine, and I do this -i, and I can seal the kernel. And right now the kernel is unbreakable. You cannot insert the modules. You cannot do anything to the kernel itself right now. There's a very good FAQ in our website. Anything contain maybe if you have any question, you can just check this FAQ first. Right now we have, after you install the leads, you have, right now we can see some testing. All right. After we boot the system, you seal the kernel, you do the more prop leads if you have used leads as a modules. And you do the leads -i. This means that you have sealed the kernel. And from the log, you can see Linux intrusion detection system started, and how many objects and how many source ACL and how many objects are in this access control list database. And you can do the cat etc shadow. You can see that the operation is not permitted. You cannot see the shadow password right now. And if you want to touch ABC in a bin directory, you can see that operation is not permitted. And if you want to remove the modules of the leads, you can see that operation is not permitted. You can do anything. You can do nothing to these kernels right now. The log will show that somebody, the PID and the UID, what kinds of users and what kind of process he used to violate this program, to violate this CAP system modules. And finally, we have a summary. Okay, the LEADS project actually is a free software effort. We have this LEADS is under the GPL, and we developed this one for free, and we do not have any support right now. All these things is by interest, and I have to thank many people because without them, there's no any. LEADS cannot go too far right now. And the LEADS actually is implement as security modules in the kernel, because we talk about the architecture, we show the attack and defense. It means that LEADS can enhance the Linux kernel security in some efforts. Finally, I want to acknowledge you, and you take your time to listen to this speech, and I want to thank the LEADS users and developers, especially the Philip and the Steve and all the LEADS users here. And I also want to thank the wonderful world of the free software. With the free software, you can do a lot of things. You can get anything you want from the internet. If you do not like it, you can just modify it. So you have all the rights. But with the commercial one, you have to pay, and you cannot do something you want to do. So I guess this is the wonderful world of the free software. With the free software support, we can develop very interesting tools to enhance our kernel. And I want to thank my employer Insure Network, which sponsored this trip for me. And finally, I want to thank DEFCON to provide the opportunity for me to present this LEADS here. All right. Any question? Thanks. Any question? Oh.
Have any of the Linux distributions expressed an interest in including LEADS in their distribution?
There's one distribution already include LEADS. There's Ingadi LEADS distribution. You can find it on www.linuxsecurity.com. There's a website, and there's a distribution made by this company.
Integration into the Linux kernel proper, is there any, is it being proposed? Plans to propose it?
Oh yeah. In the Linux kernel, the Linux security modules will go into the Linux kernel maybe in 1 or 2 months. But as modules, maybe we will go into the kernel in the future. But I don't know if I guess I will surprise. I will supply this kernel that leads to the Linux, but I don't know if he would accept it.
Has he commented?
No, I don't think so right now.
Question. Can you comment on any performance hit?
What?
Any performance hit? Any decrease in performance?
Any decrease on the performance, right?
Yeah. You're currently, whenever you call a syscall,
Okay.
you are checking some conditions.
Yes.
And that's often enough.
Yeah. For performance, frankly, I never check the performance on this list before, but somebody on the mailing list told me that he had used the server with the list support and he never saw any performance downs in any case. So I guess even if, because I do not check every system call. For example, when you open a file, I just check when you open the file. If you read or write the file, I do not check it. I just check at the very first checkpoint. Cisco? Yes, I just check the sys opened. I do not check sys read or sys write. So I guess this will improve the performance.
Another question.
Mm-hmm.
Can you verify the integrity of the kernel after it's been attacked? So can you detect, let's say somebody attacked your kernel.
Yes.
By some unknown method. Right?
Yes.
Can you verify the integrity of the kernel?
All right. If the leech found somebody trying to attack the kernel, he would. Attack the kernel has several methods. The first one is you use modules, and the second one he used the raw IOs. And so right now, all these things have been checked by the lead. So in this case, if lead found somebody trying to do things like that to insert modules kind of things, he would provide information in the log, just told that who use what kind of tools to insert or to do what kind of things. So in this case, after lead found this one, he would terminate all the operations that this program do, so it will not affect the kernel itself. In this case, he can protect the Linux kernel. So in this case, I guess the integrity could be guaranteed.
I see. So you just block the known vectors.
Yes. Yes.
Rather than try to verify integrity afterwards.
Yeah. I just everything is just terminate all this process.
Thank you.
Sure. And no? Okay, let's finish this. Thanks you take your time here. Thanks.